Tonight's presentation is by Matthew Courdier, and he will be addressing underwater vehicles like drones and gliders, widely used in the industrial and scientific world, as they allow for easy, safe and cheap access to operations. Submarines are also important in navies as they provide unrivaled operational advantages. Despite being used at depths, underwater vehicles are required to travel on the sea surface for some period of time where they are subject to wave and wind. However, most of the hydrodynamic knowledge applicable to conventional surface ships is not relevant to underwater vehicles due to their particular hull forms. Also, hydrodynamics is of critical importance as it defines the ability of the UV to carry out its mission. Hence, seakeeping resistance and manoeuvrability form the subjects of this research. Matthew is using computational fluid dynamics, or CFD, which allows modelling the fluid flow around the underwater vehicle and its hull. The variation of such parameters as the speed, wave height, or even the hull shape helps to understand the flow dynamics, but CFD also requires real-world validation, and that is carried out through experimental testing at model scale. And that is the subject of Matthew's talk tonight. But a little bit about Matthew before we start the presentation. Matthew graduated as a naval architect from NSW Bretagne in France, specialising in hydrodynamics and stability. He has worked for Naval Group as a simulation engineer, developing complex submarine energy and propulsion systems. He also has an MBA in global business management. He has worked at AMC previously on the scaling effects on submarines. Matthew's current work sees him back at the AMC National Centre for Maritime Engineering and Hydrodynamics. Matthew also won the 2020 Laurie Prandolini Fellowship and IMRS Stanley Gray Awards, both in the same year. Tonight's presentation from Matthew focuses on his research to date, and we are grateful he has interrupted his schedule to give tonight's presentation. Thank you, Matthew, and I look forward to hearing what you have to say.
Hello, everyone. Thanks, Greg. Thank you all for being here today. So indeed today I'll speak about my research and I'll try to explain why it is important and what makes it so cool as well. So more specifically, I'll speak about this seakeeping behavior of a surface underwater vehicle. So I'm aware not everyone here is a naval architect or marine engineer. So I divided my presentation into 4 parts. And at the end of the day, I think you will understand a bit better what is seakeeping, what is an underwater vehicle. I will refer to them as UVs, or maybe even some basics of hydrodynamics. So we'll start with a few definitions, and then we jump straight into my research questions, basically the problems I'm trying to address. And from there, we'll talk about the significance of the work. And at the end, I'll show you what I actually do and did in the last 2 years on some of my first results as well. So first of all, what is an underwater vehicle, a UV? Well, it can be a lot of things. This one is a military concept ship from Naval Group. And we see here a long, relatively flat object. This would be roughly 80 meters long. But sometimes we would refer to something like this. That's an exploration device, like this one from Trident Subs or other that could be used for tourism purposes, for example. So that one is more of a leisure craft. This one can bring 2 or 3 people in the water to great depth until 11,000 meters deep, really. Or we could also refer to something like this, which is a much smaller autonomous underwater vehicle that are used most of the time for research or science purposes. Or finally, we can refer to this one. This is a manned submersible, and that's probably what we all think about if we speak about submarines or underwater vehicles. So this one is the Shortfin Barracuda from a naval group. But before going further, just a reminder of what our planet looks like. So there is roughly 1,400 million cubic kilometers of water on the Earth. And this is why we use underwater vehicles. Essentially, this is because there is no other way to effectively explore, monitor, understand more than 2/3 of the world. And also more and more of humanity depends on the oceans for energy, for food, for transportation. And so the only way to effectively manage this is with machines that actually go underwater. From a military perspective, it's also the least detectable way to move anything, also to move people or to move sensors across the globe. So there is an enormous potential for underwater vehicle use. I will divide them basically into three main categories. The first one are UVs for commercial or civilian use. So this includes research, for example, or industry-related purposes, as well as tourism. So if you're interested, I believe you can rent this one to go for holidays or something. The second category are for military or naval use. And we sort them generally into two main groups, which correspond to their power generation, so either nuclear or conventional, so that's diesel engines. More anecdotic, but we can also find here mid-jet submarines, and I'll show you some pictures a bit later. They are not really conventional submarines, so that's why I'll put them in a third group. And finally, there's all the special submarines, special vehicles, which is everything else. It's quite hard to classify, but we can cite, for example, the rescue submarines like this one, which will simply go on dock on top of another submarine if it happened to have an accident and we wanted to evacuate the people inside, for example. But my research is not related to all of these underwater vehicles. Actually, I will segregate them by their shape now. And so I'm working on UVs that roughly present this shape. So basically, there's a cylindrical mid-body or parallel mid-body with a conical nose and tail. So that's pretty simple. On top of this, we can add various appendages to help with stability, for example, or steering control. So my point is that I work on a rather long and slim body, a torpedo-shaped body. And this is of importance because this is a shape that has been optimized for a very long time now, that we find today on a lot of different vehicles. So to understand where it comes from, we can go back in the past. So this is the typical shape of underwater vehicle that were used during the World War I and II. So there were no major evolutions in the hull shape between the two wars. And what we can note here is that the underwater vehicle doesn't fit the modern definition that I just gave you before. So in fact, it's not quite a submarine yet, it's called a submersible. And so yeah, they can travel underwater, that's what they were designed for, but they would spend most of their time at the surface. And that's why the design had to compromise between the shape of an object that would go underwater on the shape of a surface ship. So with a pointy bow, for example. And then during the Cold War, the US have carried out a lot of research to develop a more modern submarine because they thought that it would become a significant advantage, and it did. And so they introduced the teardrop shape, so like this picture here. So that shape resulted from a lot of hydrodynamics optimization, and they achieved a high propulsive efficiency to maximize the submerged performance at the expense, though, of the surface performance, the surface capabilities. So it's better to go underwater, and we can go further, faster for a long period of times, but it's not as good anymore for surface behavior. And that is the same shape that is most widely used today, as we can see on this picture here. So this one comes from a review, so a journal paper review of autonomous underwater vehicles. So it's quite comprehensive. But one thing that is not clear on this picture is the scale, because underwater vehicle can come in a variety of sizes. So they can come in kid size or in adult size, basically, or even in a lot of adult size. So this one here is an AUV that we have here at AMC, and it's used for research, especially for Antarctic research. And so that photo was taken in 2019, I believe, just after a dive underneath a glacier. On what is true for autonomous underwater vehicles like this one is also true for submarines. So they come in different sizes. On this first photo here, we can see 84 boats. They are Japanese midget submarines. So they measure 23 meters long on 46 tons. So that's really quite small for a submarine. On the other hand, on that photo, we can see a very big submarine. That's a Russian Typhoon class submarine, which I believe is the biggest submarine ever built. So it was also 23 meters, but in width this time, for 170 meter long on roughly 48,000 tons. So that's really a huge ship. So that's, yeah, a bit of context on the shape, on the size of underwater vehicles. So as there is a lot of variability to do research, we agreed to work on some hull shapes only that are well known. So these are both submarine hulls, and they are open source. So we can share them amongst the different research centers around the world. And that's very good because then we can compare our results. We can discuss our results with other research, discuss them on common basis, really. So the left-hand side one is called the Suboff. That's a generic nuclear submarine shape that was developed in 1989, I think, in the US. It presents some limitations. We see, for example, the aft control surfaces, so the appendages at the aft of the body are quite small. On the sail, also is quite basic in shape. Then we have the BB2, so the second picture on the right-hand side, which represents a modern diesel submarine. So this one has been developed in Australia from 2004 and then further developed in the Netherlands until 2017. So it's really the best current model hull that we can use and that we really share between the different research centers. Also, we can see on this second hull, for example, that the appendages are much bigger. So that's much easier than to turn, for example, to conduct maneuvers with that hull shape compared to the first one. Okay, so now we know a bit more about UVs. On the UVs I focused on for my research. So we can start asking questions. Why a surface underwater vehicle? Because after all, I thought submarines were meant to operate underwater, right? So yes, that's true. However, they still need to spend a substantial amount of time at the surface. So at the start or the end of a mission like this one, for example, the AUV simply needs to go back to its mothership and to be recovered by the mothership. So we need to ensure that the launch and recovery of them are possible even for adverse sea states. Or another example, during a mission, they need to go back at the surface to communicate. So either to receive or send data, for example, or even to reorient themselves with GPS. On here, the ability to travel safely at the surface gives the limits of the UV operation. So basically the limits of the mission. And for military submarines, well, they need to get back at the surface to get fresh air, for example. So I told you there's diesel generators inside the hull. To run diesel, we need air, we need oxygen. So we need to get at the surface to pump that. And the second example is also that there are people inside that hull. So we want to be sure that the accelerations and the motions of the platform always remain within acceptable human limits. And so as we can see on these last pictures, surface underwater vehicles are subject to waves, subject and create some waves. And that's important. So this video starts to show the complexities of near surface or surface simulations. We see here that the water is traveling on the hull. We see we create some waves. And so we'll be interested in the wave shape, for example, here. And so surfacing for a UV is an operation that presents a lot of risks in itself. The UV that has been designed and optimized to move underwater. Remember, I told you that since the US in 1989. So they've been designed to be underwater, and now we want to bring them back to the surface for this critical part of the mission. So its stability changes, its weight changes obviously as well. And so to be able to surface, the UV needs to be lighter. So its buoyancy force becomes greater than its weight. And all these cause a lot of perturbation on the hull and the hydrodynamics forces. So that first photo is the USS Nautilus in 1966 that had a collision while sailing at periscope depth, so just underneath the pre-surface. The second picture here, that's the USS Hartford that collided with a ship in New Orleans in the Strait of, in 2009. And the damages here were over $120 million. On that picture here is very recent since it's last year. It's a Japanese submarine that again collided with a surface ship when trying to surface. So it basically like came back to the surface underneath the ship, and then had damages to its sail control surfaces onto the sail. So this shows some examples of risk associated with surface operations for underwater vehicle. And we understand that UV need to operate safely at the surface. So another question now, if we need to operate safely at the surface, then we operate in the same environment than a normal surface ship. So we already know a lot about surface ship. So how come we don't know a lot about submarines? Well, how come the knowledge we have about surface ship is not applicable to submarines? Well, there's two things. Well, let's start with that. This is an additional level of complexity that we have for submarines that we don't know for surface ship. That the submarine needs to be able to evolve in 3 dimensions, in 3D. So here we see that submarine, well, going deeper. So the submarine traveled in 3D when the surface ship is like stuck in a 2D world on the surface of the sea. So I think that's a Vanguard submarine here. So this 3rd dimension is critical for UVs as they operate in a very narrow vertical band. And also it has been shown quite recently, so here at MC in 2019, that the surfaced UV has some particular behavior that are not quite the same as a regular surface ship and also not quite the same as its own submerged behavior. So there's 2 things in particular. The first one is what we call the negative added resistance. So the resistance of the submarine in head waves becomes negative from time to time. So the resistance is an important parameter as it gives us the propulsive efficiency that we need for the submarine, for example. So for those of you that are not familiar with that concept, just think about this. You're in a car on the highway and you put your hand through the window. So now you feel that force of the air pushing in your hand, right? Well, that's the same thing that happened in water on a submarine hull. We have that fluid resistance to the forward motion. So now think again about that, the negative added resistance. So from time to time, the water is like sucking the hull to move forward instead of presenting a resistance. So that's quite interesting, and that's also quite unique. So we can see on that graph here, the resistance coefficient equals to 0, and for some conditions, we see that it's negative. So I don't want to get too deeply in the details just yet. We'll talk about the second phenomenon, which is the motion response of the surface UV. So it's also quite particular, especially because there is a heave and pitch coupling that's different than regular surface ship. So this graph here on the left shows the typical heave and pitch response of a surface ship. So we see that we have a peak on the heave and a peak on the pitch, and both peaks are aligned. So that's what we expect usually for surface ship. Now, if we look at the same graph for surface submarine, we see this. So first thing we can see here that there are actually 2 peaks on the pitch. We can also see that the peaks are not aligned. Or actually, the heave peak is aligned with the pitch trough. So that is, even if we're not expert or if we don't understand this graph completely, we can see there are like substantial differences in the way the hulls will react to waves. So why is that important? Well, first thing first, this is the motion response of the hull to waves. So obviously we wouldn't want to operate in these peak regions where the motions would be very, very intense and very big. So on the left-hand side graph for a surface ship, there's only one peak region, so it's quite easy. If the boat travels faster, then we get away from that peak region and the motions become smaller again. For the surface submarines, on the right-hand side graph, there's a lot of peak regions. The heave sometimes peaks when the pitch doesn't, and vice versa. So it's much more complex. So what we see here is that the UV is much more susceptible to adverse seakeeping than a regular surface ship. And so that's what we call seakeeping. And so that's critical. Remember that UVs need to operate at the surface for critical parts of the mission. And this is why this research is important. So here again, for example, we see that the submarine is operating with an helicopter. So they need to be really accurate in the operations they're doing. To do that, we need to be able to understand and control the motion of the submarine. And I'm adding a few more pictures here because that's an example of real stuff that happened last week. So I just wanted to add them here. This is a training exercise from the Royal Navy in Arctic. And we can see here an Astute class submarines with some commanders operating in close proximity to the hull, that's how we call it. And here again, that's the view from an helicopter where we can see that, well, we need to be really accurate in what we do here. Let's talk now about the research impacts on who will benefit from what I'm doing. So I'm trying to answer this big question. What is the seakeeping response of a surface underwater vehicle in waves? I divided that question in 4 sub-questions. That's usually what we do when we do research because it's easier to work on smaller questions. The first one is the effect of depth. So here I want to investigate the evolution of the particular behavior I described before from a deeply submerged condition to a surface condition and see how the phenomenon evolves, basically. The second one is the wave parameters. So here I want to play with the wave height or frequency. And the 2 following ones bring a bit more variability. I will study the influence of hull shape on appendages on the seakeeping behavior of an underwater vehicle. So really what this is about is to tackle the operational surface requirements for current and future UV projects. And there are very direct outcomes in Australia, in the world today. The first one is all the defense projects with navies around the world wanting to buy or design new submarines. Also, as AUVs are becoming more and more available for research or science purposes. But not only for researchers, they also cover industrial needs as they can operate in remote or hard to access or dangerous locations and for a long period of time. And the last point is a bit different. The impact of my work is expected on both the design and the operation of an UV. So in different phases of the life cycle, really. And so when we know that a submarine design and manufacture roughly takes 15 years, and then it will operate at sea for 30 to 40 years, well, we can realize that this work has quite a significant role. And so there's 2 principal novel components to that research. First, I want to give a set of guidance on principles to designers and operators on the seakeeping abilities of a surface UV. So that include conclusions on the influence of the different part of the hull on their shape, on the motion, on resistance abilities of the submarine. And then we'll give new knowledge in the field of fluid dynamics through both a state-of-the-art, what we call the multi-phase RANS-based CFD model, so it's numerical simulations, to replicate the surface behavior of the UV in waves, and also new and improved experimental methods that allows us to test more than we could do before. And this is based on 5 new steps in the understanding of the fluid mechanics. The first one is the hull and free surface interaction modeling through a fancy type of mesh for simulations. So we call it overset mesh with boundary layer interactions. The second one is the calm water resistance of the surface UV. So we want to understand that resistance in calm water first. And then the motions. So the motion response of a fully appended surface UV in head waves. And so here we will study that double pitch behavior that I showed you before, for example. And then once that's done, we can study the resistance of the surface UV in waves. And finally, look at the relationship between the pressure distribution and the phase difference between the heave and the pitch. So that's getting a bit technical here. I'll give you some elements of methodology on them. So how we do fluid dynamics research. We basically use experiments, so EFD, experimental fluid dynamics. That's something that we do like in the real world. So we can touch the model that we put in the pool, that's physical. And then we do simulations, so computational fluid dynamics or CFD. And we often hear people saying that CFD is much faster than EFD experiments. And that's why we see more and more CFD. I don't believe this is the case. And a good example is that I spent a year developing the CFD model. And I also spent a year developing the new test rig to be able to do new experiments. So I think the main difference between CFD and EFD is that the experiments gives us a point measurement of one value at one time, where CFD would show an overall complex flow visualization, and then we can measure all the parameters that we simulated before. And also CFD is much more flexible because we can do situations that cannot be constructed in a towing tank or in a big pool. And we can do different scales. We can test designs even before they are being built. So yeah, CFD allows us to do more than only the EFD. And then we basically use the experiments to give us data points to feed into the simulations. And when we know the simulations are good and they are working, we can run different cases. And guess what? Then we go back to the experiments, probably because now we're asking new questions. We have new understandings of what's going on. So we want to measure something else or differently, or measure it at a different location or in different conditions. So that's exactly what we're doing. And that's basically the fluid dynamic research loop. So these are a few pictures of CFD model. So the first step is to create a mesh around the hull. This is a very important step as the mesh artificially creates a large number of points in the volume we're working on. And then we use all these points and stick to them the equations of the fluid mechanics. And then we use the computers to solve all these equations. So meshing is very important because if we want to be accurate in the way we resolve the equations, the mathematical equations, well, we need a good mesh. As an order of magnitude, the models I'm working with have up to roughly 10 million points. And we use, obviously, supercomputers to solve that. So that's basically using 120 computing cores and running the simulations for 5 to 7 days for one simulation. At the end of the process, we can plot results like this one or this one. So these are the CFD result of a simulation of a surfaced fully appended BB2 hull for different speeds. And what we show here is the volume fraction. So we stop on side views, but that's basically a plot of the free surface elevation, the elevation of the water around the hull. I'm interested here in simulating numerically something that has been tested experimentally before. If the CFD results match the experiments, then we know that the CFD is correct. That's roughly the idea. And then we can use it to investigate further conditions again. So what we do in simulations, we also do experimentally. And that's to get all these data points that allow us then to use the simulations. So this is the experimental setup that we are using here in the towing tank at AMC. So we can see here in yellow the submarine hull, which is 1.6 meters long. we can see in black the carbon post that holds the hull in the big steel structure. And so that post moves vertically and allows the hull to move in waves. On the big metallic structure is basically a giant load cell. So that's what we use to measure the forces in different directions. Another view here. So I put a CAD view because it's a bit easier to see, I think, what's going on. So we see the hull in the water. So the vertical structure moves on, again, the big load cell to measure the forces. And then on the right-hand side, that's a photo of the installation of the model. So all this is actually a lot of work. Installing this test rig took us roughly 3 days with 4 people involved. And you can also notice on the photo that one of the technicians actually is a diver. So he spent his days in the water to be able to attach all that and prepare all that very accurately. And then all this structure here is put on a carriage in the towing tank. So that carriage here travels above the water and drag the hull in the water. And so that's a photo of the AMC towing tank. And we can see here a bit better what it actually looks like. So that's 100 meter long for 3.5 meter wide. And the depth we're using is 1.5 meter. And we typically use the models we can see on the left-hand side wall, the yellow hulls there that measure roughly between 1 and 3 meters. I'll give you a quick overview of some results, and so what I'm actually doing. So we obviously try to compare the CFD pictures with the photos from the experiments. So here we see 2 photos from 2 different runs at the same condition, and we will look at how it matches with the simulation. I'm just putting some lines here. We see that the side wave along the mid-body have a similar hull shape. We see a bow wave with the wave run-up that goes up to the sail on the base ripple that I detailed here. So again here, so that's just a zoom of the previous pictures, really, clearly showing the water run-up above the hull. And so now we understand that this phenomenon that occurs here on a torpedo-shaped body is not really something we can see on a surface vessel. And so that's also why the knowledge we have for surface vessel is not applicable for submarines or LUVs. And so I spent basically the last 2 years to try to model this correctly, and then to try to replicate that in the towing tanks in a way that is accurate and that we can measure. And this is an example of some result graphs. So here I plot the drag force. So it gives us an indication of the resistance of the UV. And I compare here 2 different configurations, so pitch or not pitch. And this helped me to inform some choices for the CFD parameters I need. So that's a work done that's currently being published. And so hopefully you can read that soon. On here we can see the drag and drag differences for different speeds. So basically what I'm trying to show here is that when the speed get more important, so faster travel, we need to be able to have the hull moving in the 3 degrees of freedom we're interested in. So at higher speed, we see the differences between the 2 configurations get bigger. And so for example, for the last graph at 1.12 meter per second displacement, we see that we have almost 10% difference between the 2 configurations. So that basically means that we cannot simplify the model by blocking the pitch. So we need to be able, both in the CFD in the experiments, to have the hull moving with the 3 degrees of freedom. And so that's a plot of the wave field around the hull. Now remember that little graph that I showed you before. Well, that's exactly what happened. So we've done experiments and compared to simulations. And now we are looping back to experiments with a new test rig so that we developed last year to be able to test more conditions. And so now I'm working on integrating a wave component in the models. So this requires for the UV, the ability to move in 3 degrees of freedom. So that's something we can do numerically. That's also something we're trying to do experimentally. So let me show you the video from the towing tank. So that's really something that is a few days old with that new rig. So you should be able to see the video now. Tell me if not. So what's going on here is that the carriage starts to travel above the towing tank, and then we create some waves. And so now we see the hull moving in waves. And then so we will measure how much it moves with what forces, and depending on well, the wave speed, the wave height, lots of different parameters that we're playing with. Here we go. Then on the longer run, I want to study, so I told you different hull shapes. I can't help myself but to see similarities in other structures as well than purely submarines. So this, for example, is a tidal farm, so used for renewable energies. There are also surface bodies that looks like very much like a torpedo-shaped body. I'm sure it's also very important to understand their seakeeping or their motion responses in waves. So this one has been deployed at the beginning of last year in Scotland. It's the first one of this type, I think.